Chapter 8 was building off of our knowledge of moles and mole conversions from Chapter 7, but applying it in the context of an overall chemical reaction. So we actually related Chapter 7 and Chapter 6, where we looked at chemical reactions and balancing equations, to this specific chapter. We defined mole ratio as the ratio of reactants used to products created in a chemical reaction. So after we write out an equation and we balance it, and I'm going to fill in and just highlight the coefficients here, those coefficients we can read in one of two ways. We initially started reading them as individual units, as individual particles. One molecule of nitrogen is reacting with 3 molecules of hydrogen to produce 2 molecules of ammonia. Or, even more specific, for every 1 molecule of nitrogen that reacts, 3 molecules of hydrogen must react with it to produce 2 molecules of ammonia. But we can scale this up now to looking at the mole level, right? If I have many, many, many particles on the order of Avogadro's number. So those coefficients can be read as 1 mole of nitrogen will react with 3 moles of hydrogen to produce 2 moles of NH3. That is useful for us because then we can, like a recipe, figure out if I have a certain number of nitrogen and hydrogen, how much ammonia can we produce, or if I want to produce this much ammonia, how much hydrogen and nitrogen would we need. So in this example, just using pictures, I have, it looks like 1, 2, 3, 4, 5, 6 moles of hydrogen here, and I have 1, 2, 3 moles of nitrogen. And based on the ratio of the reaction, 1 mole of nitrogen will react with 3 moles of hydrogen to produce, and this is actually a really terrible image of ammonia because it's not trigonal planar. It should be trigonal pyramidal, but I'm going to go with what's there, to produce 2 moles of ammonia, which we're representing by the 2 molecules here. Now that reaction can run again based on what I have in my reactant mixture to get another 2 moles of ammonia. And now the reaction, I do have 1 mole or 1 molecule, depending on what scale we're looking at, of nitrogen left, but I have no hydrogen to react with it, so the reaction cannot proceed any further. The most we can make with this mixture is 4 moles of NH3, and I have hydrogen as my, what we defined as limiting reactant, right? That ran out first. It limited how far the reaction can go, and I have 1 mole of nitrogen in excess. That's my excess reactant or excess reagent. We'll work through some just regular problems here, but again, the biggest thing about stoichiometry was all about moles. I can only read that equation in moles. The coefficients are only mole ratio, not gram ratio. So if I'm given grams, if I'm given liters, if I'm given anything but moles, we're thinking about how can I get 2 moles of that substance so I can use the mole ratio from the chemical equation. The first example here says how many moles of nitrogen are needed to produce 18 moles of ammonia. So dimensional analysis came in handy here. I have 18 moles of ammonia. The reaction tells me that I can produce 2 moles of ammonia every time 1 mole of nitrogen reacts. Moles of ammonia cancel. I do my math, and I'm left with 9 moles of nitrogen. Right, this middle step here being the mole ratio from the equation. Second one, how many grams of ammonia will be produced if 9 moles of hydrogen react? So we're starting with 9 moles of hydrogen. Assuming it's reacting completely because they didn't tell me otherwise, the ratio in which they react and produced, it's 3 moles of hydrogen. Every time 3 moles of hydrogen react, 2 moles of ammonia will be produced. But they don't want moles of ammonia as a final answer, they want grams. But we looked at last chapter the molar mass, which is a conversion factor that will relate the moles of a substance to the mass. That's 17 grams per mole for ammonia. So if we make sure our units cancel and then we plug all of that into our calculator, we should get 102 grams of ammonia. Third example, how many grams of hydrogen are needed to react with 10 grams of nitrogen. So I'm starting with 10 grams of nitrogen. This is a red flag because I cannot use the mole ratio which I need to use until this grams of nitrogen is in moles. So I use the molar mass of nitrogen, 28 grams per mole, to convert to moles, which allows me to use the mole ratio from the equation, which is 1 mole of nitrogen reacts with 3 moles of hydrogen. And they want grams of hydrogen, so I'm going to go one extra step and use the molar mass of H2, which is 2 grams per mole. And if we plug that in, get 10 times 3 times 2 divided by 28, we should get about 2.14 grams of hydrogen. The last example says, what is the maximum number of moles of ammonia that can form when 5 moles of nitrogen and 12 moles of hydrogen are placed in a container and allowed to react? Which is limiting, which is in excess. And I really like using the icebox here, initial change end of reaction, to summarize what's going on. So if we write out our reaction, we have N2 plus 3H2 yields 2NH3. My I is initial. What am I initially starting with? None of the product, but I'm starting with 12 moles of nitrogen and, 5 moles of nitrogen and 12 moles of hydrogen. And the icebox can only be done in moles, right? So if we're given grams, we know how to convert to moles to do the icebox. The C represents change. So how is this changing as the reaction proceeds? Well, these are going to decrease in moles as they are used up, and this is going to increase, but they're going to increase in ratio with each other. Meaning, if this decreases by x, then this is going to decrease by 3x because of the mole ratio, and this is going to increase by 2x because of the mole ratio. But what is that change going to be? We can figure it out. So let's take a hypothetical. Let's assume that all 5 moles of nitrogen react. How many moles of hydrogen would react with it? Well, the ratio is 1 to 3. So 3 times as many moles of hydrogen will react as nitrogen. If 5 moles of nitrogen react, 3 times that amount is 15, which I don't have. So that tells me the nitrogen can't be used up first. I wouldn't have enough hydrogen to react with it. The hydrogen must be used up first, all 12 moles. How much nitrogen will be used up? Well, it's a 3-to-1 ratio. So a third the amount of hydrogen that's used will be how much nitrogen is used. So 12 divided by 3 is 4. I do have 4 moles to spare. So 4 moles of nitrogen will be used with 1 mole left over. If my change is 4 and 12, in ratio here, it's going to be 8 moles of nitrogen. And because I started with nothing, I have 8 moles of ammonia that form. So I've just answered all of those questions in one shot. We can produce 8 moles of ammonia maximum. My hydrogen is my limiting reactant because it was used up first, it ran out first. And my nitrogen is excess, it's left over, and there's 1 mole of it left over. This little mole map is handy not for sort of walking through reactions, because you're not going to have this on the final exam, but it's a good visual for all the different types of conversions we looked at throughout the year and that you can do and should know how to do. And again, the central idea here is using the balanced equation to go from moles of one substance to another. But of all the possible things we can be given, we should know how to get from all of those things to moles. If we're given mass, we use the molar mass to get to moles, and then molar mass to get back out if we want mass again. If we're given volume, we could use, in this chapter, we used 22.4 liters of a gas is equivalent to 1 mole, but that was at STP. In a later chapter and in a later video, we'll go over the ideal gas law that will also save us with gases reacting if we have to do stoichiometry and the conditions are not STP. And then if we're dealing with particles, then we have Avogadro's number that can help get me between particles and moles. So let's just look at 2 more problems here before we wrap up this review video. A student reacts 40 grams of hydrogen with excess oxygen and produces 300 grams of water. Find the percent yield for this reaction. So first thing to do is write out an equation. Second thing to do is to balance that equation, make sure it's balanced. We have 40 grams of hydrogen with excess oxygen. So no icebox needed here. This one's a pretty straightforward dimensional analysis stoichiometric conversion. 40 grams of hydrogen, we're going to convert to moles first, 2 grams per mole. And then the mole ratio of hydrogen to water, which is just 1 to 1. And then we need mass of water to compare. So that's 18 grams per mole. And if we calculate that, we get 40 times 2 times 18 divided by 4. We get 360 grams of water. Now this is your theoretical yield. That is theoretically, if everything went perfectly, how much you should be able to form. They're telling us the student only produced 300 grams. So to find the percent yield, we take the actual yield over the theoretical yield, and we multiply by 100. 300 divided by 360 times 100, we should get about 83.3% yield. So that's how efficient that reaction was run. We produced 83.3% of what we should have been able to. And in the last problem, you have 31.4 grams of hydrogen and 334.12 grams of oxygen. How much excess reactant will be left over? So this screams icebox, right? When we're talking about limiting reactant, excess, all of that stuff. So I'm going to write out our reaction again, just so we have it here. I'm going to balance it again, so we have our coefficients. And then I'm going to set up our icebox. Okay. Remember, we have to do this in moles. So they're telling me I have 34.1 grams of H2. We can convert that to moles quickly by dividing by the molar mass of H2, which is 2. So I have 17.05 moles of H2. I have 334.12 grams of oxygen. If I divide that by 32, which is the molar mass, we get 10.44 moles of oxygen. And then I'm not starting with any water. What is my change going to be? Well, again, run hypothetical. Doesn't matter which one you pick, we're going to get the right answer either way eventually. If all of the hydrogen was used up, right, all 17.05 moles, half the amount of oxygen would have to be used, right? So if we do 17.05 divided by 2, that's 8.5. Do I have enough of that? I do. So I just found out what my limiting reactant was. 17.05 moles, if that's used up completely, half that amount in oxygen will be used up, 8.525. 10.44 minus 8.525 leaves me with 1.915 moles. And we don't actually care about this because they didn't ask me how much water is made. They just wanted how much excess reactant will be left over. So 1.915 moles of the excess will be left over. If they wanted grams, we can multiply it by 32 grams per mole to get grams, but they didn't specify a unit. So I would leave it like that. We could check the other way. Like if you checked oxygen first, if 10.44 moles of oxygen was used, you would need twice as much hydrogen to be used up, and you don't have, right? You need over 20 moles, and you only have 17.05. So that's how you work those problems. Again, you have to use the method you see best. I think an icebox is a really, really efficient and convenient way, especially when dealing with limiting reactant. When you have a lot of questions to answer, you can answer a lot of them at once. So this brings us to the end of Chapter 8, which is stoichiometry. You should be ready to take your Chapter 8 throwback quiz.